Welcome back. In this video, I want to talk about something called limiting cases, which is a very useful trick that's used by most people who study physics, yet it's something that's very commonly overlooked in most physics classes. The idea behind limiting cases is that when we're studying physics, we can use our intuition to make predictions about what's going to happen in a particular problem. So we can say what's going to happen when a length increases or decreases, or a mass increases or decreases. And the idea behind limiting cases is that we're going to consider the limits, the extreme cases, where we can not only make qualitative predictions, but we can actually make quantitative predictions. So to kind of give you just a bit of an understanding of how this works, I want to go ahead and look at a few examples. So the first example says, during a test you're asked to calculate how quickly a box will accelerate down a frictionless ramp that's at an angle theta. And you can't remember if the acceleration down a ramp is g sine theta or g cosine theta. So this problem is asking us to use limiting cases to figure out which of these formulas is correct. So just to make sure you have an idea of what's going on, I have over here on the right is a picture. So we have a box sitting on a frictionless ramp that's at an angle theta, and we're trying to figure out what this acceleration is going to be. So right away, we already have some intuition about what's going to happen. For example, we can see that as this angle increases, the acceleration down the ramp is going to become faster and faster. And from this alone, we can already figure out which of these two answers is correct, because only one of those two answers increases as the angle increases. The other one's going to decrease. Obviously, the acceleration down the ramp does not decrease as this angle becomes steeper and steeper. But because we're talking about limiting cases, I want to consider the two limiting cases to this problem. So as we can see, as this angle increases, the acceleration is going to become faster and faster. Eventually, we're going to reach a limit where the block is not even really accelerating down the ramp anymore, it's just falling. And we can see that this happens when the angle of this ramp is going to be 90 degrees. And when the angle of the ramp is 90 degrees, the box is basically just going to be in free fall. So the acceleration down the ramp is just going to be the acceleration due to gravity, which is 9.8 meters per second squared. So that's when theta is 90 degrees. Now the other limiting case happens in the opposite scenario. Now as you can see, as the angle decreases, and as this ramp becomes shallower and shallower of an incline, the acceleration down the ramp is going to become slower and slower. Eventually, we're going to run into a scenario where the box isn't even really on an incline anymore. It's just on a flat surface. This happens when the angle is equal to 0 degrees. And in this case, obviously, the acceleration isn't going to be, it's going to be 0 meters per second squared, right? The box isn't moving anywhere. It's on a flat, surface. It's on a table. So these are our two limiting cases. They're the extreme cases where we already know what the answer is going to be without doing any calculations. So using these two limiting cases, we can figure out which equation is the correct one. So we had two things. It was either going to be g sine theta or g cosine theta. So if we consider when theta equals 0, we have g sine of 0 degrees. And in this case, we know the acceleration has to be 0. Well, sine of 0 degrees is 0. Cosine of 0 is 1. So this would be g. So looking at these two answers, we can see that the acceleration of the block down the ramp has to be g sine theta, because obviously when the angle of the ramp is 0 and the box is sitting on a flat surface, my acceleration down the ramp is not the acceleration due to gravity. Similarly, when we consider the other limiting case, we have a similar scenario. So sine of 90 degrees is 1. So in this case, we get g. But cosine of 90 degrees is 0. Now obviously, when a box is just in free fall like this, my acceleration is the acceleration due to gravity. It's not going to be 0. So again, in both of these scenarios, g sine theta agrees with the quantitative predictions that we were able to make. Now let's look at another example. This example says, consider two masses, m1 and m2, which are supported by a string which hangs over a massless pulley. the string cannot stretch. Therefore, when one mass moves up by a distance delta x, the other mass has to move down by the same distance. And we're asked to identify all the limiting cases and determine the acceleration in each of these cases. So again, here's a picture on the right just kind of showing you what's going on. So we've got a mass m1 on one end of the string and a mass m2 on the other end of the string, and the string passes over a frictionless pulley. So just looking at this, if we kind of go with this m1 as being more massive than m2, we already have some intuition of what's going to happen. If m1 is more massive, then the box is going to accelerate down like this. Now, just looking at this, we can also see that as m1 becomes more and more massive, the acceleration is going to increase. And as m2 becomes smaller and smaller, the acceleration of m1 is also going to increase. Now, the limit occurs if m1 is much, much bigger than m2. In this case, we can basically ignore m2. We can ignore this mass here if it's much, much smaller than m1. And in this case, we just have a box that's in free fall. So, if m1 is much, much bigger than m2, the acceleration is just going to be the acceleration due to gravity, which is 9.8 meters per second squared. A similar limiting case occurs when m2 is much, much bigger than m1. If m2 is much bigger than m1, we can ignore m1. We can just treat it like it's not there. So m2 is just in free fall. So if m2 is much, much bigger than m1, my acceleration is again going to be the acceleration due to gravity. And you'll notice I put a negative sign there. The reason I did that is because I'm considering this direction, when the mass moves like this, to be the positive direction, and I'm considering when the masses move like this to be the negative direction. Now the third limiting case is a little bit trickier. Now if we consider these two masses, as the masses become closer and closer to each other, the acceleration is going to become slower and slower. Eventually, when m1 is equal to m2, we can imagine setting it up where both of the masses are just perfectly balanced and none of them are moving at all. So we can see that if m1 was equal to m2, my acceleration has to be 0 meters per second squared. So these are our three limiting cases. So this is the last example I want to look at, and basically it's just going to combine the previous two examples. So we're just asked to identify the limiting cases for this scenario I have drawn here on the right. So again, just like the previous problem, if m1 is much, much bigger than m2, we can ignore m2. So if m1 is much bigger than m2, we just have a block accelerating down a frictionless ramp. And in this case, we know the acceleration. It's going to be g sine theta. That's what we saw in the first example. In the other limiting case, if m2 is much, much bigger than m1, we can ignore m1. We can treat it as though m1's not there. And in that case, m2 is just in free fall. So if m2 is much, much bigger than m1, my acceleration would be minus g. Again, if I assume that this direction is positive and that this direction is negative. So I think I'll end the video there, and in the next video we'll talk about some tricks that you can use on the AP exam to try to answer some of the multiple choice questions a little bit quicker.